one predictor variables in the model, there are usually more issues you have to worry about. One important issue is the actual sum of squares. So when we have more than one predictors in the model, when we decompose the overall sum of square, the total sum of square, we could actually decompose the overall sum of square into quite many terms, and each term could indicate the contribution of individual variables, individual predictors. So last time we have considered two extreme cases in regression analysis. In one case, the two predictor variables are unrelated to each other, or you can say they are independent to each other. If that happens, then we have this table. So it's on page 22. We have the calculated actual sum of squares for this kind of example. Okay, we notice SSR x1 given x2 is exactly the same as SSR of x1. Okay, notice these two terms. How these two are calculated? Let's refresh our memory. We know how to compute SSR x1. This is easy. We can just fit a model which includes one predictor variable, which is x1. Okay, so from that model, we can compute the usual regression sum of square, and that SSR is equal to this number, 231. Okay, so this number is easy to calculate. And for this number, how should we calculate this SSR x1 given x2? So in order to compute this number, we actually need to feed two models instead of one model. In the first model, we will fit a model which only contains one predictor x2. Okay, and from that model, we can calculate the residual sum of square and the regression sum of square. We can keep these terms. And then we fit another model which includes x2 and also x1. So that the second model includes both terms, x1 and x2. And from the second model, we could also compute SSR and SSE from the second model. And we can take a difference between the two models, SSR and SSE. For the two models we just fitted. And that difference will be this SSR, x1 given x2. So this SSR is computed to be the sum of square regression due to x1, conditional on the presence of x2. Conditional on x2 is already in your model. Okay, so if x2 is already in your model, the expected sum of square, the expected variation that can be explained by x1 would be this number, 231. And this number is exactly the same as the model which doesn't include x2. The variation explained by x1 is still equal to 231. Okay. So this kind of results can only occur when x1 and x2 are uncorrelated to each other. x1 and x2 has no correlation. So the contribution from x1 is always the same, no matter you include x2 or not include x2. So this contribution is reflected by SSR of x1. And similarly, the order doesn't matter. Which one you call x1 or x1, which one you call x2, doesn't matter. So in the second, so for this kind of construction, if you consider SSR of x2 and SSR of x2 given x1, we notice the sum of square are still the same. So because x1 and x2 are uncorrelated, so the contribution of x2 will still be the same to y. Okay, no matter x1 is included in this model or not. So the presence of x1 doesn't affect the contribution of x2 in this case. Okay, so this kind of situation, this kind of results can only be expected when x1 and x2 are totally uncorrelated. when there has no correlation at all. So last time we also look at another extreme case.